Microphone is not working.
All right, very sorry about that. I touched the power strip with my toe and shut down my computer like a fucking idiot. So we were asking, how can I make this substitution, u equals ln x, in this integral? So I'll just go ahead and write out my little substitution box. If u is equal to the ln of x, what is du?
1 over x.
1 over x
dx.
dx. Very good. All right. And because this is a definite integral, we need to change our bounds. So I need to figure out when x is equal to 1, what is u? And when x is equal to e, what is u? All right, so who can help me out with the first piece? When x is equal to 1, we know u is the ln of x, so u would be the ln of 1. What is that? What is the natural log of 1?
1.
0.
0.
0, right? Because
That's right.
2 to the 0 is equal to 1. Right, and when x is equal to e, u would be the natural log of e. What is that?
1.
That one. Okay, very good. So my new integral is going to go from 0 to 1. The cosine of the ln of x is going to become the cosine of u. What do I do with the dx? What can I replace this piece by? Maybe in this step. I'll just write it as dx. So we haven't replaced that yet. So I've changed my bounds. I plugged in the u to my integrand, but I haven't done anything with this differential yet. And I don't have any 1 over x's floating around in here. So what should I do?
Can't you do cosine u over x dx?
Not quite. Not quite, but you're on the right path. So I need to remember what we did if we didn't see right away, we would solve this for dx, right? This is how most people learn it in the first place. You solve for dx, then plug that in and try to cancel. So if I multiply both sides by x here, then I get x du is equal to dx. So if I wanted, I could write this as integral 0 to 1 cos of u times x du. But that's also a problem because I've still got this mixture of variables, right, in both of these. In some sense, the bottom one is getting better because I've gotten rid of the dx. I now have a du, but I still have this x. Let's come back to that very first example we looked at today. If after plugging in everything, I still have some of the old variables floating around, what do I do?
Couldn't you make it e to the u?
Very good. So, old variable persist. Solve the substitution for the old variable. So what was my substitution? I had u equals the natural log of x. How do you solve this for x? What's the procedure? You're right that x is going to be e to the u, but what's the procedure? How do you get a variable out of a logarithm?
You raise it to the power of like the base.
Yeah, you exponentiate both sides using the base of that logarithm. So I would get e to the u equals e to the ln x. And then the e to the u is just e to the u, but e to the ln x is x. So here we know x is the same as e to the u, and it's not a matter of guessing. We have a clear procedure. Now we are done. This becomes the integral from 0 to 1 cosine of u times e to the u du. And this is an integral we don't know how to do yet. All right, that's why I said we're going to stop short on this one. I'm just going to make the substitution. We're not actually going to solve the integral because I don't know how to find an antiderivative for something like this. It's a little tricky. It's quite sneaky. This requires a special kind of integration by parts called looping integration by parts. And that's one of the things I'm going to show you when we begin chapter 7. All right. Integration by parts you can think of as like the integral version of the product rule, right? Like you've got a product rule for differentiating. If I asked you to differentiate cos u times e to the u, you would use the product rule. Similarly, if I asked you to integrate it, you need the integral version of the product rule, and that's integration by parts. Turns out this is a special kind of integrand. It's called a damped harmonic oscillator. And those require looping integration by parts. We'll talk about all that when we get to chapter 7. So this is our final answer for this problem. We have now successfully made that substitution because every single piece is just in terms of the new variable. I've changed my bounds. We are Gucci. All right, shit like this happens all the time. Shit like this where you've got a substitution, you know it's the substitution you want to make, but it just doesn't look like it's working. So you take your old variable and you solve for that old variable in terms of the new variable based on your substitution, just like the very first problem we did today. Any further questions on U substitution before I move to 6.1?
When you solve for, like when we try to find x, did you go through the u or the du?
U.
U, okay.
Yep. So I did do some work solving this relation also for dx. When I wanted to plug in for my dx, I had to solve for dx, so I knew what to plug in for. That's this x du you see right here. Right. This came from solving this for dx. But having done that, which is like the regular Calc 1 thing to do, right? When you make a U sub, solve for dx, plug in, and then usually you try to cancel. Well, here nothing canceled. So I had an x left over. And when we have an old variable left over, then you go back to the original U equation and solve that for x. All right. Any other questions about U sub? Okay, then. We're going to begin now on section 6.1, which is areas between curves. Just another quick thumbs up react if you've done this thing. Whose Calc 1 class covered 6.1, areas between curves? Okay, okay, okay. Oh wow. All right, this is impressive. I'm glad to see it. In the past, most of the time, my Calc 2 students had not seen this. We're going to move pretty quickly through this section, if that's okay. The basic idea is this. That given two curves, y equals f of x and y equals g of x, I can try to find the area between them. So I'll call this one f. And this one g. if you specify an interval like AB, and you want to find the area between these two curves, regardless of whether one is positive or the other is negative, it really doesn't matter. The area we're after here is this stuff. The way you would do this is by integrating the upper function minus the lower function. Okay, bunch of ways to think about it. If both functions happen to be positive, then you can think of it like you're going to find the area under f and then subtract the area under g. Or if, as I've drawn it here, the upper function is positive and the lower function is negative, you'd think of it like I'm going to find the area under f. And then the regular integral would calculate the area bounded by g, but as a negative thing. So when you subtract it, it becomes positive. 1,000,001 ways to try and describe this for you. I will just tell you that this blue shaded area here would be equal to the integral, definite integral from a to b of f of x minus g of x dx. If you kind of want to see it from first principles, the idea is if you draw in a little Riemann rectangle here at an arbitrary point, you draw in a little strip that you think of as being a representative Riemann rectangle in your Riemann sum. So I'm looking at some value in here, xi. Then up here, this is the point xi comma f of xi. Down here, this is the point xi comma g of xi. So the height of the rectangle is f of xi minus g of xi. So the area of the rectangle would be that times delta x. So your Riemann sum looks like sigma I from 1 to n f of xi minus g of xi times delta x, which becomes this when you convert it to an integral, right? And you take the limit as n goes to infinity. That's your kind of one-line explanation. Now, I'm not going to make you work directly with Riemann sums. And we will work with sums later in the class. We're going to talk about infinite series, power series, stuff like that. You will need to work with the sigma notation there. We'll work with it a lot. But here, I'm comfortable discussing things in terms of integrals, and I hope you are too. There are two ways I can complicate this picture. I could have these curves touch each other somewhere between A and B. So maybe the upper and lower switch places. Then the upper minus lower thing doesn't really work because you don't have a consistent upper or a consistent lower. Or I could have these not be expressible as functions of x. I could have instead maybe a function of y and a function of x, or some combination of other stuff like that. So I'm going to show you how to handle those situations. But first, I suppose we should take a look at a nice straightforward problem. Let me pull up your textbook and see if I can find some examples here that are tractable. Actually, I've got one in mind. Yeah, I know. We'll start with an easy one. Let's begin by find the area between y equals cos x and y equals sine x from x equals 0 to x equals, we'll go out to just pi over 4 first. Now I'm hoping that you guys know what sine and cosine look like, hoping quite intensely. But just in case, let me mark this over here as pi over 2. Cosine, you know, is equal to 1 when x is 0 and is equal to 0 when x is pi over 2. We have a tangent line coming out here like this. We have a tangent line coming in here like this. So the cosine curve over this region is going to look something like that. And then it would, you know, continue down here like this and go on and on. The sine curve is equal to 0 when x is 0 and is equal to 1 when x is equal to pi over 2. And a tangent line here looking like this and over here like this. All right, and then he continues on and on doing his thing. So this is sine x. Yeah, this is sine x. And this is y equals cos x. And I'm zoomed in just from 0 to pi over 2. You know, sine continues over here like this, cos continues over here like this. So the area I'm looking for here is from 0 to pi over 4. And pi over 4 is the spot where sine and cosine are equal to each other. So the area between cosine and sine from 0 to pi over 4 is just this little piece. Everybody comfy with this? So my blue shaded area here you integrate the upper function minus the lower function from a to b, which in this case is from 0 to pi over 4. My upper function there is cosine. My lower function there is sine. And now to evaluate this integral, we just need to find an antiderivative and plug in bounds. That's nothing too bad. An antiderivative for cosine is positive sine x, because the derivative of sine x is cos x. An antiderivative for sine x is negative cos x. So this negative and that negative will play with each other and give us a plus cos x. And this needs to be evaluated between bounds. And finally, plugging in pi over 4, I know each of these is root 2 over 2. And I'll subtract what we get when we plug in 0, which is 0 plus 1, right? Sine of 0 is 0, cos of 0 is 1. All this basic trig shit, you gotta know cold, right? There's no room for not knowing your unit circle in this class. You must know these things. They need to be like 0 time things. Root 2 over 2 plus root 2 over 2 is 2 root 2 over 2, or just root 2. So this is the square root of 2, and this piece is 1. So that's the square root of 2 minus 1.
So do we have to draw out the question to see which one's on top?
Yes, yeah, that's one of the first kind of things that you're gonna realize as you solve these problems, is that you need to sketch the graph to know what you're doing. That's important. If you don't sketch the graph, you won't know which one to put above the other. And what's more, they can trade places. So the next thing I want to do is the same problem, but from 0 to pi over 2. And I'll show you how we would set that up. So what if I want,
Professor, for when we're just to clarify, when we have when we find the integral for the area of the shaded region, we find the antiderivative of what's inside the parentheses, right? And then we solve by plugging in the interval, right?
yeah, once you have set up this integral, the way you evaluate any definite integral, we're leaning on the fundamental theorem of calculus here. So the way you evaluate anything like this is to find an antiderivative for the thing inside, and that's what this is, and then evaluate between the bounds. So you plug in your upper bound, that's this, and then you plug in your lower bound, that's this. But yeah, that's correct. You find an antiderivative for the thing inside, and then plug in the upper bound and the lower bound and subtract them in that order.
Thank you.
Of course. So let's go from 0 to pi. Here's a question, right? Look down at the bottom there. What if I want to find the area between sine and cosine? Instead of from 0 to pi over 4, I want to go all the way from 0 to pi. I'm specifically choosing pi here. The example in the book goes from 0 to pi over 2, because you could actually make a symmetry argument. You could say that the little slice over here is the same as the little slice over here, and then just argue that if you double this, you'll get that. So I don't want any shortcuts like that. So let's say we're going to go from 0 to pi. I'll resketch the problem, but here's the question we're going to evaluate next. How do I find the area between these same two curves from 0 to pi? I'm going to turn the page in just a second, sketch the new question. Is there anything else we want to ask about this example before we move on? Okay. So the general idea is if your curves are both functions of x, then you integrate the upper minus the lower. If they happen to change places, which is going to happen here, find the area between y equals cos x and y equals sine x from x equals 0 to x equals pi. I will sketch those curves from 0 to pi as best I can. We call this 1, I'll call this -1, which means pi is about 3 times that. Out here, which means pi over 2 is halfway. And the multiples of pi over 4 are here. Let me use a little bit of color here. Let's see, do I have enough colors to do this? No, maybe not. No, that's okay. We'll not use the color then. So sine of 0 is 0. Sine of pi over 2 is 1. And the sine of pi is back to 0 again. So the sine function will look something like this from 0 to pi. And then he will continue as it does. And the cosine function, cos of 0 is 1, cos of pi over 2 is 0, and cos of pi is -1. So the cosine function is a tangent here like that, tangent here like that, tangent here like that, something like this. And then he'll continue on in the fashion that he does. All right, so up here is cos x, over here is sine x. And my region now is from 0 to pi, so I'm going to chop here, and I'm going to start here. So I'm looking for this piece. And all of this stuff. All right. The idea is that these guys, they trade spots at pi over 4. So remember the big idea is that you want to integrate the upper minus the lower from wherever to wherever. From A to B. Yeah, so you want to integrate the upper function minus the lower. But here cosine starts out as the upper and sine as the lower, and then at pi over 4 they switch, and sine becomes the upper, cosine becomes the lower. So if the functions switch places, you need to split up the integral. Or split up the problem into multiple integrals. So, right, so here I would consider the 0 to pi over 4 separately from the pi over 4 to pi. So this time my shaded area is equal to the integral from 0 to pi over 4 of cos x minus sine x dx plus the integral from pi over 4 to pi of the upper minus the lower here, which is sine x minus cos x dx. And although we may want to try and combine those integrals or something, we can't. We can't because they have different bounds. You got to handle each one on its own. Thankfully, the first one we've already done. I know that this is the square root of 2 minus 1. We just did that. So I'm going to come over here and separately do this guy. The integral from pi over 4 to pi of sine x minus cos x. It's going to be a very similar thing. Antiderivative for sine is negative cosine. Minus an antiderivative for cosine is positive sine, so it's minus sine x. And then we evaluate this from pi over 4 to pi. Now the cosine of pi is -1, so this is -1 minus the sine of pi is 0. And then when I plug in pi over 4, I get -√2/2 minus sine of pi over 4 is also √2/2. Okay, so just be careful with your negatives. -1 is +1, minus 0 is 1, minus the second bracket here, -√2/2 minus √2/2 is -√2. So this guy is 1 plus the square root of 2. So you've got the square root of 2 minus 1 from the first piece, and 1 plus the square root of 2 from the second piece. So the blue shaded area is equal to, I'll rewrite it, integral 0 to pi over 4 cos x minus sin x dx plus the integral from pi over 4 to pi sin x minus cos x dx is square root of 2 minus 1 plus 1 plus the square root of 2. And you see the ones eat each other up. And you just get 2 times the square root of 2. So this piece I am taking over here. All right. And that's basically the whole story for areas between curves where both curves are functions of x. Integrate the upper minus the lower. If they happen to swap places, then you'll have to split up the problem into multiple integrals. And the key to all of this is drawing the graph. So you need to get good at graphing these things by hand. And here's a strong recommendation. Strong recommendation. As you work the homework problems, graph the fucking things by hand. If you're dead stuck and you really can't get it or you really don't trust your graph, sure, go ahead and check it in Desmos. But at least try to graph it by hand first and really put in some effort because you need to have strong graphing skills in this class. I will make you graph things like this on the test. You will not have Desmos or a graphing calculator on the test. So you need to get to a place where you can graph this stuff by hand. You guys are Calc 2 students. It's important that you're able to do this stuff. This is stuff that generally we would expect out of pre-calc or trigonometry students to be able to graph. So certainly I should be able to expect you guys to graph it. I just ask that you seriously practice graphing. Yeah, Shing, if you've got to bounce, you got to bounce. That's okay. I understand. Just make sure you follow up and watch the video later. Okay. So the last thing I want to talk to you about here in 6.1 is how to handle the case where the curves are not functions of x. Turns out that's not a difficult thing to do. You just kind of turn your head sideways. So here's two other curves, x equals y squared and x equals 7. Neither of them are functions of x. They do both happen to be functions of y. The first guy is a quadratic function of y, and the second one is a constant function of y. Neither of them are functions of x. So the stuff we just said really doesn't apply. I'm going to go ahead and work through this specific example, and then I'll show you the sort of general rule for this other case. X equals y squared. You can think of it as y equals the positive and negative square root of x if you're having trouble remembering what that graph looks like. Or you can remember that it's the same as y equals x squared with your head turned 90 degrees. Looks like this, right? Y equals x squared, x equals y squared. You're reflecting everything over the line y equals x, which in this case turns out to be the same thing as, rotating 90 degrees to the right. And then x equals 7 is a vertical line. Okay, so here's the curve x equals 7, and this parabola is the curve x equals y squared. The area I'm after here is this area. To see how we're going to do this, we should ask why we integrated the upper minus the lower in the other cases. In the other cases, we integrate upper minus lower because the upper function is the one that has the larger y value. The lower function is the one that has the smaller y value. Another way to say that is the upper function has the larger output and the lower function has the smaller output. So in order to get that height and have that come out positive, you subtract the larger thing from the smaller thing. Well, here your outputs are x values, and you know x increases as we go to the right. So since x is getting larger as we go to the right, our outputs are getting larger as we go to the right. So here, we integrate with respect to y. And the integrand will be the right function minus the left function. Because the rightmost function is the one with the larger output. In other words, if you want to think of the Riemann rectangles here, we can do that. I can pick a generic point on the y-axis, call it yi. Draw in the Riemann rectangle. Have that generic point. This point right here is, we call y squared f of y, and x equals 7, I'll call that g of y. Then this would be f of yi, comma yi, and this over here would be g of yi, comma yi. It's the same sort of vibe, but you're going to want to integrate right minus left. And then instead of imagining that rectangle is moving left to right, you imagine it is moving up to down. So sort of all your Riemann rectangles would be horizontal in this. So what's this function over here? And of course, the width of your rectangle there would be delta y. So your blue shaded area here is going to be the integral of the right function minus the left function. The right function here is just the constant function 7. And the left function is y squared. The sort of width of your Riemann rectangle is delta y. So in the limit, that would become a dy. And then you have to figure out two other things here. You have to figure out these intersection points because those are going to be your bounds. Right? You want to integrate from whatever this is to whatever this is, which are y values. So we need to also, and you'll find that you have to do this with the other problems too, the vertical oriented ones. You have to find intersection points often. All right. So to do that, I just set the two functions equal to each other. That would mean that y is equal to plus or minus the square root of 7. So this guy is negative square root 7, and this guy is positive square root of 7. So your integral here would be the integral from negative square root of 7 to the positive square root of 7, 7 minus y squared. And that integral is done dy with respect to y. So if your little strip goes in side to side, then you're doing a dy integral. And if your little strip goes in top to bottom, you're doing a dx integral. Again, the way you figure this out is by drawing the picture. You got to draw the picture. And you see if I turn this back like this, it looks just like the other problems, right? This would be like the line y equals 7. This would be like the curve y equals x squared, and you would integrate the upper minus the lower from whatever this is to whatever this is. Same shit's going on here. Okay, it's really just a change of perspective more than anything else. How do we do the integral? Well, that's not hard. Fundamental theorem of calculus says find your antiderivative. Both of these follow from the power rule. And if you wanted to, you could make use of some symmetry. I won't do that this time, but eventually we will. And then when I plug in here, I get 7 square root of 7 minus 1/3 times square root of 7 cubed is 7 to the 3/2. And when I plug in the negative square root of 7, you get 7 times negative square root of 7 minus 1/3 times, that would be negative 7 to the 3/2. Sorry, that doesn't work like that. No, that would be minus 1/3 times the negative square root of 7 cubed. Yeah, sorry about that. The negative is getting cubed, but it's not under the root, so you can't write that as negative 7 all to the 3/2. Okay. This we can clean up. 7 root 7 minus 1/3, 7 to the 3/2 minus, and then over here, this negative will distribute. This is negative 7 root 7, so we'll have plus 7 root 7 minus minus here makes plus. What are we going to have all together? How many minuses do we have? So this guy is here, right?
Shouldn't there be a square root on the 7 for the 7 square root 7 minus 1/3, then parentheses square root 7 to the 3/2?
No, so the square root of 7 I've incorporated in here, but 3/2 power, that 2 downstairs is the square root.
Oh, okay.
And then I'm just trying to sort out the minus signs we hit here. So when you cube the negative square root of 7, let me clear it. Let me back up a step just to make sure we don't get into trouble. So I'll leave this minus out here and we'll say this is negative 7 root 7. And then here I've got negative 1/3 times negative root 7 cubed. If you cube the negative square root of 7, then you get negative 7 to the 3/2. So that will be plus 1/3 times 7 to the 3/2, like this. Okay. Yeah, this is good. So square root of 7 is 7 to the 1/2. Negative 7 to the 1/2 all to the 3 is still negative because the negative cube stays negative. And then 7 to the 1/2 cubed is 7 to the 3/2. Then that negative and this negative make that positive. And then finally, we'll have one more negative coming from out here, which will make this positive and this negative again. So you get 7 square roots of 7 minus 1/3 7 to the 3/2 plus 7 square roots of 7 minus 1/3 7 to the 3/2. Oh, it's okay. All right, and then you can combine these. You recognize 7 root 7, 7 root 7 as 14 root 7, and minus 1/3 7 to the 3/2 minus 1/3 7 to the 3/2 as minus 2/3 7 to the 3/2. The fact that those pieces match up so nicely hints at the symmetry argument we could have used here. But I don't want to do too much of it. It's okay, little one. Sorry, my son's starting to wake up. He's getting a little temperamental. All righty. I think that is time for today. So this is where we're going to go ahead and wrap up. Let's see. I have you guys on Friday again also, right? This is a Monday, Wednesday, Friday. Yeah. Okay, perfect. So on Friday, we're going to solve a few more practice problems, and I'll also go over section 6.5, which is average value, since we didn't get to that today. So go ahead and get cracking on that homework. If you have not started on that yet, you really need to. It's super important. And then on Friday, we'll solve a few more of these area between curve problems, paying special attention to the ones where you have to work with respect to the variable y instead of respect to the variable x. Remember, draw the graphs by hand. Draw the graphs by hand and draw in your little Riemann rectangles. This is actually a really good idea because in the next few sections, 6.2 and 6.3, we're going to take stuff like this and we're going to start rotating it about an axis. And the whole trick there is going to be to imagine just rotating the strip. So draw your graphs by hand and draw in your little Riemann rectangle, your little Riemann strip, and see if you can understand what's going on with your integral as it relates to the geometry. All right, more practice next time. If you want to talk, come see me in office hours or send me a Canvas message. Otherwise, I'll see you all on Friday.